Here we go with part 2 of the Honors Chem Mid-Year Review. And again, just as a reminder, I'll not be posting the actual questions on the slides. You have those in your packets or in your book. So I'm just going to be putting up the answers and any other information that you really need to have in order to solve the problem. So here we go. The first question comes from page 181. This is number 15. And these are some molarity questions determining the concentrations of various solutions. So part A, we have 5.623 grams of a substance. That substance has a molar mass of 180 grams, 1 mole per 80 grams. And so if we have 5.623 grams, that comes out to 0.070 moles. And we're going to create 250 milliliters or 0.250 liters. So in terms of moles per liter, we do 0.07 divided by 0.250 and we get 0.28 molar. Part B, we have 184.6 milligrams. You can convert that to grams if you want, just make it 0.1846. Or the alternative is when you calculate the molar mass, you just make it in terms of milligrams, so it would be 242,192 milligrams. So that equals 7.622 times 10 to the negative 4th moles, and that's put into half a liter of solution. So that means we're going to end up with 0.00152 molar. Part C, if we had 0.1025 grams of a compound with a molar mass of 63.546 grams per mole, then we would have approximately 0.001 moles in 1/5 of 1 liter, which means we would have 0.005 molar solution. Number 17 on the same page. We're trying to calculate the concentration of various ions in some solutions. So if we have 0.15 molar calcium chloride, all you have to remember is that when these ionic compounds dissociate, any multiples of ions, like the Cl2, are going to dissociate as well. So you get double the amount for that particular ion or polyatomic ion. So in this case, for the Ca, for the calcium, we would have a concentration equal to the concentration of the solution. And then for the chloride, we would have a concentration that's double the concentration of the solution, so 0.3 molar. For B, 0.26 molar solution of aluminum nitrate. So the aluminum is going to have the same concentration because there's just 1 aluminum per mole. So that's 0.26. The nitrate, though, there are 3 moles of nitrate ion for every mole of solution when it dissociates. So you get 3 times the concentration, or 0.78 moles. In the next one, we have 0.25 molar potassium chromate. And since there's 2 potassiums per mole, the concentration of potassium is twice as much, so 0.5 molar. The chromate, this whole thing, Cr2O7, is a polyatomic ion as a unit, so that is going to have the same concentration as the solution because it's not going to dissociate, so 0.25 molar. Finally, on this problem, if we had 2.0 times 10 to the negative 3rd molar aluminum sulfate, then we would have, for the aluminum, the number is going to be double. So it's going to be 0.004 molar. And then for the sulfate, it's going to be triple the concentration, so 0.006 molar. Moving on to number 21, still on page 181 here. This is a question of how much solution we would have if we wanted our solution to contain a specific number of moles or a specific number of grams. So again, the concentration is in moles, not grams. So first thing we have to do is figure out 0.350 grams is how many moles. Well, to do that, 1 mole is 80 grams. And when you multiply those together, or sorry, divide, you get 0.004 moles. And that, we want to know if it's a 0.1 molar solution, that means 0.1 mole per liter, then how much solution would contain 0.004 moles, which is our 0.350 grams. So our X is the volume. And when we do that out, we find that it would be 0.04 liters or 40 milliliters, either one. I didn't specify the unit. Number 23, still on page 181. This is basically questions on how to either dilute stock solutions or create solutions from solids. So we really need to figure out how much of a substance needs to be dissolved in a given amount of solvent, which in this case is 2 liters, or if you have a solution of a high concentration and you want to lower the concentration, how much would you have to dilute it? How much would you have to start with in order to get it diluted to the right volume with the right concentration? So in the first one, we are given that we want 0.25 molar, but we want 2 liters of it. So altogether we want 0.5 moles, and 1 mole of the compound has a mass of 39.99 grams, which means we need 19.995 grams. Rounding off, we would need 20 grams of the substance dissolved in 2 liters of liquid, or water rather, and that would give us the 0.25 molar. In the second one, we're trying to find out how much stock solution, which is 1 molar, so that's M1V1 equals M2V2. So what we know is our desired molarity, the final molarity, and the final volume. What we don't know is what volume do we need to start with if the starting concentration is 1 in order to get a final concentration of 0.250 molar, and if we want 2.0 liters of that. Well, when you do that out, you find that you would need your V1 to be 0.500 liters. So you start with half a liter of stock solution, dilute it down to 2 liters, and your concentration would be 0.25. Okay, if we want 2 liters of 0.1 molar solution, that means we want a total of 0.2 moles, and 1 mole of this compound has a mass of 242.192 grams, which means in order to create 2 liters of 0.1 molar solution, we would need to dissolve 48.4 grams of the substance in that 2 liters. And then the last one is another dilution. If we start with 1.75 molar, how much would we need to start with of the concentrated solution if we wanted to end up with 0.1 molar solution and a volume of 2.0 liters? And that comes down to our starting volume. We need 0.114 liters, or 114 milliliters. So the next ones we're going to have, we're moving on to page 182, question number 29. And this is looking at some mixtures of ionic solutions, whether or not you'll get a precipitate out of it, and that would ultimately determine whether or not you have a reaction or not. Because if there's no precipitate, there's no reaction. So this is number 29. The first reaction is solution of aqueous barium chloride and aqueous sodium sulfate. Well, when you switch around the ions, you get sodium chloride, and these are not going to be balanced. That's not really the key. The key is what are the combinations, and then you end up with Ba barium sulfate. So are any of those compounds insoluble? If you look up on page 152, it has a chart with the summary of the solubility rules, which is going to be very important for you to know. And we find that both of these new combinations are soluble. So there's actually no reaction here. There's no precipitate. Both of these compounds would be aqueous. Okay, for the second one, we have lead nitrate, and we have potassium chloride, and that will produce potassium nitrate and lead chloride. Potassium nitrate is soluble. All alkali metals are soluble. All nitrates basically are soluble, so that's an easy one. The lead chloride, if you look at rule number 3, will tell you that this combination is insoluble. So this is going to be your precipitate. For the third one, we've got silver nitrate and sodium phosphate, which would produce, if you rearrange that, you'd end up with sodium nitrate and silver phosphate. And according to rule number 6, silver phosphate is insoluble, so that's going to be your precipitate. That's rule number 6. And the last one on this problem, sodium hydroxide and iron nitrate would produce iron hydroxide and sodium nitrate. Again, the sodium nitrate is definitely soluble. The iron hydroxide is not soluble. That will be your precipitate, and that's according to rule number 5 in the chart. So now we're on to page 183, and this is where we're getting into the oxidation and redox reactions. So number 59, it's asking you to identify the oxidation number for bromine in each compound. Well, in order to do that, you have to look at all the other stuff that's in there and then work out what the difference between the oxidation states of any of the other things are, and add the oxidation state of bromine to balance everything out. Hydrogen, that's going to be a +1 oxidation state, which means that bromine must be -1 in order for that to be neutral. For the second one, you've got hydrogen, oxygen, and bromine. Well, oxygen is -2, hydrogen is +1. That means that bromine here must be +1 in order to balance out the oxygen. Bromine, Br2, any element by itself has an oxidation number of 0. If we have hydrogen, bromine, and oxygen, 4 oxygens gives you a -8. The hydrogen gives you a +1. In order for this to be balanced, this must be a +7 for bromine. And finally, we've got bromine with fluorine, 3 of them. Fluorine is a -1, so the total there is -3, which means the state of bromine must be +3. Okay, so for number 61, we're looking at these reactions and trying to figure out A, are they oxidation reduction reactions? Because they may or may not be. You have to take a look at each oxidation number and find out what's changed, if anything. And then we're going to try to figure out which things are being oxidized and reduced. So methane and oxygen produce carbon dioxide and water. So let's look at the oxidation numbers here. Hydrogen is +1 for a total of +4, because there's 4 of them, which makes the carbon a -4 in the methane. And then the oxygen is elemental, so it has an oxidation state of 0. On the other side, you've now got the carbon combined with the oxygen, which has a total of -4, 2 times -2 for oxygen, which means this carbon has a charge of +4, an oxidation state of +4. And then over here, you have oxidation of -2 for oxygen, and then +1 apiece for the hydrogen. So if you look, the carbon has gone from -4 to +4. So it's had an oxidation change of 8. It's lost 8 electrons altogether. So that loss of electrons is oxidation, so this has been oxidized, which makes it the reducing agent. And then the oxygen has gone from 0 on the left to a -2 state on the right. So it has been reduced also by a total of 8 electrons, which makes the oxygen the oxidizing agent. Alright, so 61B, we have zinc and hydrochloric acid, and that produces zinc chloride and hydrogen gas. So zinc as an element, 0. Hydrogen as an element, 0. Those are easy. In the hydrochloric acid, chloride, the halogens have charges of -1, which means this hydrogen has a charge of +1. Over here we have 2 chlorines, each with a -1, so that's a total of -2. The zinc has a charge of +2, or an oxidation number of +2. So the zinc has lost 2 electrons going from left to right. That means it has been oxidized, which makes it the reducing agent. And the hydrogen has gone from +1 to 0, which means its number has been reduced, which means that the hydrogen is the oxidizing agent in this reaction. So taking a look at the reaction part C, we have the dichromate ion, charge of -2, and hydroxide ion, charge of -1, yielding 2 chromate ions and hydrogen gas. So the hydrogen gas element, 0. The dichromate, you've got 7 oxygens, so that's a -14 altogether. The overall charge is -2, which means the chromate has an oxidation number of +12 or +6 each. The oxygen here in the hydroxide is -2, which makes the hydrogen +1. So that works. And then on the other side, we have 4 oxygens in the chromate, so that's -8. The overall charge is -2, which means this chromium is +6 oxidation state, and we've already said the hydrogen has 0. So this one, if you look, you've got chromium in a +6 state on both sides. The hydrogen does get reduced from +1 to 0, but there's no oxidation half. Okay, the oxygens have remained at a -2 state, the chromates have remained in a +6 state. So this is not a redox reaction. Part D. So we have oxygen, O3, or ozone, plus nitrogen monoxide, producing oxygen gas and nitrogen dioxide. Okay, so here we have ozone is still elemental oxygen, even though it's O3. It's just another state or another version of elemental oxygen. The elemental oxygen here has a state of 0. So we've got to look at the two nitrogen compounds. In this case, we've got a -2 for this oxygen and a +2 for this nitrogen. On the other side, we've got two oxygens, which is a -4, which means this nitrogen has to be +4. So the trick here is that the nitrogen has gone from +2 to +4. It has lost 2 electrons, so it has been oxidized, okay, which makes it the reducing agent. And you think, well, I've got oxygen on both sides, it's 0. I've got oxygen on both sides, it's -2, but you have one of the oxygens from the ozone, went from O3 to O2. Well, that oxygen went over here, and so it went from 0 to -2. So that one oxygen atom has been reduced. Okay, so one of the oxygens was reduced in this transition from O3 to O2 and from nitrogen monoxide to nitrogen dioxide, which makes this oxygen the oxidizing agent. No big shock there. All right, for 61E, we have hydrogen peroxide decomposing to water and oxygen. Okay, elemental oxygen has a state of 0. The oxygen here has a -2. The hydrogen has +1 each for a total of +2. On this side, we have two hydrogens, +1 each. They can't be anything else, which means that those two oxygens have a oxidation state of -1. So this is a strange type of reaction called a disproportionation. And it's actually a case where we have hydrogen's state doesn't change. So nothing happens to the hydrogen in terms of redox. However, we have two oxygen atoms that go from -1 to -2. So they are being reduced. So two oxygens are reduced. The other two oxygens go from -1 to 0. So two of the oxygens are oxidized. So this is a case where one substance acts as both the oxidizer and the reducer and gets oxidized and reduced. So tricky one here. Just pay attention to the fact that it could in fact be the same substance that gets oxidized and reduced in the same reaction. It's still a redox reaction, but it's this weird thing called disproportionation, which, by the way, is also what we're going to get for part F. We have copper chloride. It's copper 1 chloride. And it's going to produce copper 2 chloride and elemental copper. So the elemental copper is 0. This is a -1 for this chloride, which makes this a +1 for that copper. Well, in this one, we still have -1, or a total of -2, for the chlorine, and then that means that the copper here has to be +2. So one of these chlorines went from +1 to +2, so that one was oxidized. And the other copper, is it copper, not chlorine? Copper went from +1 to 0, so it was reduced. So this is another one of those disproportionations where you have one substance that's acting as both the oxidizing agent and the reducing agent. It's being oxidized and reduced and sort of the element gets, in this case the copper, one atom goes one way, one atom goes the other, one gets oxidized, one gets reduced. So the same thing in both cases. So moving on to page 233 to some gas law stuff. For the chart, I'm just going to go ahead, and all of these are ideal gas law problems. You're given some combination of pressure, volume, number of moles, and temperature, and you have to fill in a missing variable. And they're all in atmospheres, so the value for R, this is number 35 on page 233, the value for R in all of these problems is 0.0821 because all of them are in atmospheres. So in the first setup, we're looking for volume, and we're given a number of moles of 2. We're given the 0.0821, it's the ideal gas constant, and we're given a temperature of 155 Celsius, which is 428 Kelvin. All that's going to get divided by a pressure of 5.00 liters, atmospheres rather, and we're trying to find the volume, which is 14.1 liters. For part B, we're trying to find the number of moles. The number of moles is found by the pressure times the volume divided by the gas constant times the temperature, which was 155 Kelvin, and that gives us a number of moles of 0.047 moles. C, we have the temperature that we're after. Temperature is the pressure times the volume divided by the gas constant times the number of moles. Do that out and we get a temperature of 677 Kelvin. That's already in Kelvin. When you do these problems to find the temperature, it automatically comes out in Kelvin. But if you're given Celsius, you have to convert to Kelvin first. If you're asked for Celsius, you have to convert to Celsius at the end. All right, the last one, we're trying to find the pressure. Pressure is the number of moles times the gas constant times the temperature, which was 75 Celsius or 348 Kelvin, divided by the volume of 2.25 liters, and that is a pressure of 133 atmospheres. Okay, also on page 233, number 41, we're given a problem in which we have an initial volume. So this is volume and pressure. So P1 V1 equals P2 V2. And the initial volume is 2.0 liters at a pressure of 760 millimeters. And then the pressure drops to 500 millimeters. And we want to know what the volume would be. Well, V2 is 3.04 liters. And the question says if the maximum capacity of the balloon is 2.5 liters, would it burst? So the answer is yes, because it would need to be a volume of 3 liters in order to accommodate that pressure. Page 234, number 43. We're given a pressure and a temperature, and then told that the temperature goes up, and to find the new pressure. So this is P1 over T1 equals P2 over V2. Make sure, T2. So when we're doing temperature again, always make sure you convert to Kelvin. So this is 13.7 megapascals at a temperature of 296 Kelvin. So what would the pressure be if the temperature rose to 723 Kelvin? And we would find that that would be 33.5 megapascals, which makes sense. The temperature more than doubles, therefore the pressure should more than double, so that works out. Number 51. We have this reaction. This is a little bit of gas stoichiometry. So the reaction is C6H12O6 plus 6O2 yields 6CO2 plus 6H2O. And we want to know what volume of oxygen would be required in order to react with 5 grams of the carbohydrate. So first thing we need to do is figure out how many moles. Everything goes through moles. All roads lead to moles. So in order to figure out how many moles of oxygen we need, we got to do some stoichiometry. 5 grams, the molar mass of the compound is 180 grams, so that means we've got 0.027 moles, and the ratio of oxygen to the sugar in the reaction is 6 to 1. Right? Coefficient of the unknown, coefficient of the known is 1. So 6 times that number of moles would be 0.162 moles. So that's how many moles of oxygen we have, or we need. And then the question is, what's the volume? And we're given a temperature and a pressure that is not standard. So we need to take the moles. We do happen to have a handy formula called the ideal gas law, in which we can take moles, pressure, and temperature and convert it to volume. Because the volume, we've got the P times V equals nRT. And so the volume is equal to the number of moles, which we just found out, times the gas constant. We are given the pressure in atmospheres, so we can use 0.0821. Temperature is 301 Kelvin, and the pressure is 0.976 atmospheres. And when we do that out, we find that we would need 4.1 liters of O2 to react with that amount of the sugar. The second part of the question asks what volume of each product would be produced by the same reaction. And fortunately for us, the ratios are equal. So for every mole of oxygen, you get a mole of carbon dioxide and a mole of H2O. So if we produce 0.162 moles of oxygen, or we use 0.162 moles of oxygen, we would get the same number of moles of both carbon dioxide and hydrogen, which means that you would get 4.1 liters of each. So 4.1 liters of CO2 gas and 4.1 liters of H2O gas. And finally, on page 235, we have problem number 61. And we're trying to determine the density of two gases. Those two gases are in a container, and we are given a pressure and a temperature, and we are not given a number of moles, so we can assume 1 mole of each, as it mentioned on the cover sheet for the problem set. Since you're not given an amount, you can just make it simple and assume 1 mole of each. So in order to find the volume, given these conditions, if we have a total of 2 moles of gas, 1 mole of each, and we're going to need the gas constant here for torr, which is 62.3637, temperature of 358 degrees Kelvin, and the pressure is 758 torr, we would find that we'd get a volume of 58.908 liters. Now this is for 2 gases, 1 mole of each. And again, the nice thing about the gas laws is that it doesn't matter what the gases are, all that matters is how much there is of each gas. Since we've said there's exactly the same number of moles of gas, that means that we can split that number in half and say that each gas has a volume of 29.54 liters, 454 liters. With that, and we said that there's 1 mole of each. So the silicon tetrachloride would have a molar mass of 169.885 grams, and the volume of that gas is 29.454 liters, which gives you a density of 5.8 grams per liter. And then for the silicon with the hydrogen and chlorine, it would have a molar mass of 135.435 with the same volume. So it has a slightly lower density of 4.6 grams per liter. So there are your final answers there. That's the end of the review for the mid-year exam, and we'll see you Monday.